by Dr. Manjaiah, and he has given the previous lecture on the powder production methods and the characterization. And during this lecture, he is going to talk about the various case studies of metal additive manufacturing and his experience where he did his postdoctoral, say, at abroad. So he is going to share that also. So yeah, it is over to you, Manjaiah. You can.
Thank you, sir. Thank you.
Yeah, you start.
Yeah. Very good afternoon to everyone. Once again, I'm welcoming for this my second session. Here I'm going to talk about the metal additive manufacturing, the insights, and as well as the more case studies which I have worked on the real-time projects. Almost I have worked several real-time projects which are already used in this novel research applications, and as well as the Styria Aerospace. They have manufactured some of the air duct parts and as well as the outer structural parts which has manufactured from the additive manufacturing. Already they are already applied and already using in the aerospace applications and as well as some submarine applications. These case studies I am going to discuss and give the more insights of the metal additive manufacturing. What are the difficulties? What are the problems when you are manufacturing, and how to address those problems? We are going to discuss those in more aspects of this metal additive manufacturing process. Coming to this, the metal additive manufacturing process, as I have discussed in my earlier lecture also, we are having three major metal additive manufacturing processes are there. The one is direct energy deposition process, the powder bed fusion technologies, that is the SLM or SLS process, as well as bind jetting process. In DED itself, we are having this laser direct energy deposition process and as well as the wire arc additive manufacturing process. Means we are categorized in terms of the feeding material. Either we are feeding the material in terms of powder or in terms of wire we are feeding. Based on this, we have categorized the metal additive manufacturing processes, and most widely used is the powder bed process and as well as this direct energy deposition process. In these aspects, in the metal aspects, we are already aware. This is the fourth day because you are already aware that how this 3D printing works and how it is categorized based on what ASTM standard and what is the recent terminology which we are using based on this ASTM 52900 standards and all. As our professor C.B. Paul sir has given a more insights of the indigenous developments of this AM machines, what we are developing in India, that is with respect to the DD machines and as well as with respect to the powder bed machines and all. To see the process, I'm not going to much discuss about the how process works because many of the speakers have discussed the how the process works and all. In this process, from the design model to the real-time part, we are going to manufacture. You can see this is the theoretical design will be there, and till the finished part, we are going to manufacture from the additive manufacturing process. In this process, whenever we are designing the CAD model, that is with respect to the existing CAD model, or we can develop our own the ideology that can be made to functionalize the parts. We can able to revise with respect to the functionality aspects using the certain topological optimization tools and by analyzing the whatever the stress analysis or the load carrying capacities or as well as the factor of safety considering the functional part material. This theoretical model we are designing, and that model is given into the path generation, that is generating into a number of slices using a CAD model or slicing software. Then we are supplying into the machine, that is the manufacturing process. And then the machine is going to manufacture the whatever the given data in the 3D CAD format, that is in the format of the STL file format, that is going to manufacture the part. This is the manufactured part in the metal process and all. If you see here, this metal part is manufactured. This will be having lot of the residual stresses, thermal stresses, and as well as the distortion and the surface profile will be there. Because we are also assume that the whatever the component or the part is manufactured, we assume that this is the ready to use part. We are directly using that part, assuming that, but still there are so many challenges are need to be addressed whenever the part is manufactured from the AM process, either any of the metallurgy manufacturing process, because some certain post treatments are very much required in the additive manufactured parts. Even though it is a near net shape manufacturing process, we need to address some of the certain things, because whenever the part is manufactured, it will be having some staircasing effect. It will be thermally or really stressed, because repetitive heating and cooling is going to take place in the part manufacturing whenever in the AM process. That needs to be addressed before going to the part, the final part is to be used. For that, we need to have the post-processing techniques. You can see it is mentioned here. There are several post-processing techniques are there. The hot isostatic pressing, it is one of the hipping process, and as well as heat treatment process to relieve the stress relieving, annealing to improve the microstructural properties and all, and as well as machining to get the required tolerances and geometries, and as well as laser polishing or either abrasive flow finishing or chemical polishing or electrochemical finishing. These are all the post-processing techniques we are using to achieve the required geometrical tolerances as well as the mechanical properties and to relieve the residual stresses, and as well as the required surface finish to achieve wherever we need to have in the medical application or in the aerospace application. With respect to these things, you can see in this metallurgy manufacturing process, we are using the different kinds of heat sources. We can use the laser or electron beam or as well as arc, as a which we are using in the TIG welding or in the MIG welding. Similar kind of arc energy source also can be used in the metallurgy manufacturing process. And in the case of the displacement, we can go with the robotic systems, and both with the robotic and gantry system, that is the mixed whatever we are having. You can see here, this is the CNC machines. That CNC machines are modified as a laser direct energy deposition process, because the function of this, the milling head, instead of the milling head, they are adapting as a the laser deposition head. Here we will be having the same controlling systems, the same kind of the bed systems where we can hold the our workpieces and all. Similarly here, the mechanism will be there, only we are adding instead of the milling head, we are adding the deposition head, which is controlled with the z-axis movement and as well as the powder feeding system, and also along with the laser which is coming through the coaxial nozzle and all. And in these systems, we are having so many number of process parameters. Here I have just highlighted only the major process parameters which are related to the quality of the part which is going to be manufactured from the metallurgy manufacturing process. The major thing is laser beam, how much the energy density we are supplying, that is the laser power, scan velocity, and how much quantity of powder we are feeding when you are using in a laser direct energy deposition process, and as well as the shielding gas and how the solidification is taking place. That is depends upon the cooling rate and as well as the temperature gradient. Based on this, we are going to reveal what kind of microstructure, what is the quality of the parts we are going to able to manufacture with this metallurgy manufacturing process. These are all the major the process parameter which relates the quality of the parts which are going to fabricated by this metal AM process. Coming to this, when we are talking about this AM process, the metal AM process, we are having a big deal with respect to the, even till today we are having so many hurdles or challenges with respect to the metal AM process. Because when it is started, we can assume that we are able to manufacture any kind of the product or the part which we are having in our mind. We can able to manufacture those. Yes, we can able to manufacture those parts, whatever we are having in our thoughts, are to required for the functional aspects and all. But there are some certain the challenges, and also we think that what components we can able to manufacture that is can be ready to use or not. Yes, it is can be manufactured, it can be used for the ready to real time applications and all. Why? Because we are having a wide availability of this CAD and CAM software. We are having a free to design whatever we need to want to functionalize, that can be easily designed or modeled because of the n number of and free availability and freedom to design what component we want with the available modeling and the CAD software, and the improvement or developments in the automation and component technologies. Because there is a day-to-day the development is taking place in this automation and these component technologies, and as well as the growing library of printable material. Day to day, the metals, when it is started, the material was using very few materials. We are started with only stainless steel materials, or with only the aluminum materials or titanium metals. But today we are having even the intermetallic materials that can be made with this additive manufacturing process, and as well as other kind of ceramic materials, even the functional grade materials can be made with these kind of this AM process, metal AM process, because the development are growing of library of these printable materials, and as well as the major industry and the government investment. Even till today, the investment with respect to this AM process is growing more and more. Because when it is started majorly, we are buying almost all the metal AM machines from outside the country, that is from the abroad, from the Europe or from the USA. We are buying the machines, but now the machines are manufactured in India itself. The AM machines, whatever this metal AM machines, the either the LDD process or with the powder bed process, people have started with the manufacturing their own indigenous machine because of the investment from the industry and as well as the government investment to develop this kind of the revolution of this AM process to commercialize this and conventionally replace with whatever the conventional manufacturing process which are not possible to manufacture the complex parts that can be made with this AM process and the freedom to operate enabled by this patent expiration. When you are the taking about this the FDM process or steel lithography process or extrusion or bind jetting, there are so many patents are expired. That's why we are having a freedom to operate the enabled of this the patent expirations and the momentum and confidence and the creative vision. In this AM process, we are having the confidence and the creative visions are more to develop what kind of the components in aspects of this aerospace, medical, and as well as the submarine applications in the naval applications. And it is a very fast prototyping technique. None other manufacturing process can able to make the fast manufacturing of these prototypes. Only this AM is having a fast manufacturing prototype can be made with this AM process. And also the complex geometries can be able to manufacture with the AM process. If the complexity is going more and more difficulties, it is highly difficult to manufacture with any other conventional manufacturing process. But because of this AM process, we can able to manufacture highly complex part with the AM process, either metal or polymer AM process. Even the multiple material, what I was tracking, the multi materials or the FGM systems that can be made with this AM process. We are having only few the conventional manufacturing process to make the FGM process, FGM components, functionally grade materials like the powder metallurgy techniques or centrifugal casting. These kind of the few techniques are available to manufacture the functional grade materials, but the AM 3D printing process, especially the DED direct energy deposition process, we are having so much of the the freedom to design or develop the functionally graded materials because of the availability of the n number of the hoppers which contain the different kinds of the powders that can be fed into the nozzle to melt or to deposit the mixed mode of layers in the mixed mode of materials in the single layer itself that can be made with this kind of the availability of these DD systems. And we are having a enhanced performance of these AM systems and all. And as well as the low volume manufacturing. When we say about this low volume manufacturing, it can consider as a personalized components. The customized, personalized component can be made with the same process. When you are thinking about this medical applications, because from person to person, we cannot able to use the same type of component or one component or one the geometry, because from person to person, patient specific components are required because either the teeth or the crown or the hip implants or the knee implants or any the vertebral stents or any of the rods which are required from patient to patient, it is going to be changing because in the market no other manufacturing process is available to manufacture the personalized manufacturing components that can be made with this AM process. That's why this AM is a very big deal aspects in the metal item manufacturing process with respect to the components we are going to manufacture. If you see here these two major examples here, this is very recently during this 2021, the Porsche might have heard this the sports car. It's a Porsche car has been manufactured. This the piston head, which was made by this titanium material, the piston head with the a Trump laser, and this piston heads were earlier manufactured by this the forging method. That piston head was redefined. You can see this was topologically optimized because this was entirely a solid component when you are making with a forging operation, casting and forging operation. But because of the availability of the n number of modeling software and the topologically optimized software, where we are considering the safe factor of safety with considerations, and as well as with the consideration of the required stress distribution and the load carrying capacity analysis based on the simulations, we have designed this the topologically optimized piston head that was made with this spot bed fusion technology with the titanium materials, and this the piston head is going to save the 10% lighter than the compared with the piston which is made with the forging process. The weight is reduced because of the topology optimization, and even the horsepower which was gained by this the topologically optimized piston head is 30 horsepower is gained in the 911 GT RS, the Porsche car, because the quality and as well as the strength and as well as the lighter in the part. That's why the horsepower gained in the machine, in the car is what the engine is more. And if you see in the right hand side, this is already since when it was we are talking about 1992 and all. This G leap nozzle jet engine. It was made by this portable fusion technology. This the leap nozzle tip it consisting of more than 34 number of parts. When you think of manufacturing this component with a this is the fuel injector nozzle tip. When you make with this kind of component, which was 34 number of components cannot be made with a single component in any conventional manufacturing. You can go for casting or the forging, or you can go for machining or any other the conventional manufacturing, because it consisting of so many complex parts and as well as very finite nozzles, very finite holes are there. That is highly complex and difficult to manufacture with the conventional manufacturing. And even to manufacture the n number of components, 34 number of components to assemble that part, hardly it will take more than the 6 to 8 weeks of time. But with the availability of this, the advanced technology, this AM, the metal AM process, you can able to manufacture this component in 8 hours. That is the major benefit we are having, that is going to reduce the cost of manufacturing and as well as the emission of the CO2 emission from the aircraft. That will also improve the efficiency of the aircraft and also minimize the CO2 emission from the aircraft. And it is already we are using in the aircraft. More than the 30,000 aircrafts are using this kind of the additive manufactured the fuel nozzle tip from the, and G is having a patent, and they have developed this kind of the deep nozzle tip of this aircrafts. If you see this, the benefits and complexity free means what is the major benefits with respect to this AM and how it is complex free. You can see this is the conformal cooling channel. This is the cooling channel. This cooling channel, if you want to make this conventional manufacturing method, we need to have this kind of the machining methods, and we can be assembled made with a number of parts and all. The conventional machining with the cooling channels. And it was numerically simulated and optimized with the topologically optimization and numerical simulation. Wherever the temperature distribution is taking place, that was highlighted from this numerical simulation, and that was numerically optimized and then topologically optimized and can be made in this form. This part can be directly made with this metal AM process that is going to gives a new geometric shape. That is not at all possible in this conventional manufacturing methods. That can be made with this the 3D printing process and all. It is makes more easy and possible to design the advanced cooling channels that the tools or the components for the better and as well as the therefore the reduced cycle time of this manufacturing process. And if you see here in the right hand side, the graph is many of the PPTs, many of our the professors, the earlier speakers has given these insights of this. You see the cost versus complexity. When to use this additive manufacturing process and when to use this conventional manufacturing process. Whenever the production is more, the number of components is required more than 10,000 of components, and even the complexity is very less. In such cases, you can go and directly use with this kind of the conventional manufacturing methods, and also make sure that the process is efficiently able to manufacture such kind of components or not. And if the complexity is very high, even if you want to make with the conventional manufacturing process, yes, it is possible to manufacture, but the time requirement and the cost of production of such components in the conventional methods is very, very high. But with respect to the AM process, the metal AM process, if the complexity is more, there is no constraints or there is no the increase in the cost of manufacturing. The cost of manufacturing will be same, but even though complexity is very high, that can be easily freely manufactured from this AM metal AM process. That's why it is a very complexity free for the manufacturing of any complex components with the AM process. That is the major advantage of this, the metal additive manufacturing process. And you can see even the complexity is less, the cost will be same. Even the complexity is more, the cost is also stable. That's why the complexity is more, even the cost is not going to vary with the additive manufacturing process. There is no additional cost is going to be added, even the complexity is changing from simple to the highly complex. That is a major the benefit or advantages of this the metal additive manufacturing process. And if you see the another examples which is related to the medical products, you might have seen this dental crowns or bridges or the implants, the skull implants or the knee implants. These parts, when you come across with these dental crowns or the bridges, to make with this the conventional method, we are going to make a standard the type of the crowns or the bridges, but that is not at all suitable for patient to patient. Where this AM is playing a major role in customization, highly customized parts, because with the help of these 3D scanners, we are having so many number of 3D scanners are available. With the help of the 3D scanners, can able to scan the patient specific the requirement, the crowns or bridges, and that can be redesigned or edited with the help of the available softwares, the mimics or with the magic softwares, and that with the help of this DICOM file we can edit and we can redesign and we can able to print such type of the crowns or bridges from this the printed from this metal. And even if you see this, the market scenario, over more than 30 million crowns or the copings or the bridges have been already made with this the metal AM process, that is the SLM process, over this last duration of the 60 years. And also the market share is increasing day by day. The experts, the estimation of this more than 10,000 copings are produced every day using this AM process. But if you want to make it that a conventional manufacturing process, it will be very hard and takes more than 1 week of time. The production is faster when you comparing with these kind of the customization parts. Even 450 crowns per day can be made, but while the dental technician can make only 40 crowns per a day in such kind of the complex customized parts. Even these implants, you can see in the implants where we need to have the highly geometrically fit and with respect to the particular material, that kind type of the skull implants or the knee implants with a highly modified surface finish is required, or the surface structure is required, that can be made with the metal AM process, either this DED technology or with the powder bed technologies. Whenever we need to have a highly lattice structures, the porous structures, we have to go with the powder bed fusion systems and all to manufacture such kind of highly porous materials. Because whenever we are talking about this biomedical application, we need to have the highly porous materials, because what we are having this bone is highly a porous structure, and that porous structure is varying from position to position. The density is varying from the center to outside or the outside. That is where we need to requirement of this medical components made with this AM process and all. This is the major requirement of this the metal AM process. And this additive manufacturing going to replace this conventional manufacturing method for this customized products or customized parts. Even you can see, with respect to my experience, we have worked with respect to these are all the metals in this metal additive manufacturing. These are all the real-time industry-oriented parts we are made with this aluminum, the stainless steel material, maraging steel material, titanium materials, even with the uh, aluminum duramold with the, as well as the Astella 709 and as well as Astella X. You can see these are all the microstructure and how this simulation was analyzed, and how this and which we are doing with research in collaboration with University of New Brunswick. We have done so many research aspects with respect to these materials in the metal additive manufacturing process. Even with this, the metal additive manufacturing process, you can see here in the powder bed system, what kind of parts, the functional, the surface patterns. You can see these kind of the surface patterns, this Limpa Corporation having the patent of this kind of the knee implants. These knee implants was made a patent from this Lima Corporate, and with the EBM system, electron beam melting additive manufacturing system, they have developed these kind of the implants. And even with this internal cooling channels was having a patent with GE. The internal and having a patent with this, the cooling conformal cooling channels, and as well as the injector head made with different kind of the complex the porous structures with the required design that is made with the GE and all with the conformal cooling channels. Even with this topology optimized shapes, you can see this is the aerospace brackets, either the door brackets or wherever the hinges are there. These kind of hinges or the brackets are made with this the topology optimization, and was made with this the metal laser deposition process, or with the SLM process, or with the WAM process and all. And Raghu is having a patent of this kind of topology optimized aerospace brackets and all. Even this D as this leap we have discussed, and the lightweight structures for the medical and aerospace can be made with this the SLM process and all. And with respect to the metals, as I have discussed, it is the innovation characteristics. Means the whatever the characteristics we need, that kind of innovative characteristics can be made with this kind of metal AM process, and with the redesigned shape, structure, and as well as the surface properties. Even with the internal, the modified structures, overall the supply chain can be made with this kind of the AM process. And as well as this AM, with respect to the metals, is similarly kind of a welding or sintering process. The mechanism of the process is similarly like a welding or the sintering process. There are several different processes for the metals are existing. You can see here the powder bed, that is the powder feeding technology, laser metal deposition, or the wire arc additive manufacturing process, the powder bed fusion system, that is the select laser melting system, and as well as the electron beam melting system. Even though this the binder jetting is having, but these four leading are going to working till today with the metal manufacturing of the components with this process. With respect to the DED systems, you might have aware that this how DED works. DED we can use as a powder or the wire as a feeding material. It is a direct energy deposition process. Is primarily used to repair the existing or worn out parts, or we can add some of the features on the existing parts itself or the structures. Some of the turbine blade is worn out, we have to repair, but there is no other conventional manufacturing methods are available to repair the turbine blades. But with the availability of this DED technology, we can repair such kind of the damage or worn out the turbine blades. That is the major the availability or the motto of this the direct energy deposition to add additional features for the existing components, or we can repair the components, or we can able to manufacture the even the 3D near net components also can be made with this kind of a process. And this the melt pool, how this the DED production process works. The DED works when the melt pool is formed on the metallic substrate with a laser beam interaction. When the powder is feeding through the coaxial nozzle into the melt pool where the laser is directly interacting. In this, the laser is directly interacting, and the powder is fed through this coaxial nozzle. The laser beam interaction is taking place, and then the molten pool is formed on the flight mode, and then the solidification is taking place. That molten pool is formed. This is how the bead is formed in the case of the direct energy deposition systems. And even if you see at this, the powder melts and forms the a fusion bond between the substrate and as well as the powder and the fusion between the workpiece material and the molten material. In these the DED systems, we can use the kind of the 4-axis or 5-axis motor system. Even with the robotic arm, we can use these kind of systems and all in the DED process and all. And you will be having a deposition head will be there in the DED system where we are supplying the coaxial in the nozzle. The powder feeding systems will be there from the hopper, and as well as and this process is less freedom for design when you are comparing with the powder fed systems, because here the powder is coming through the nozzle where the nozzle head is moving for a certain geometrical aspects and all. That's why there is a certain constraints or limitations are with respect to these kind of the machines. Even the post deposition heat treatment may be required for this kind of the direct metal deposition fabricated parts and all. Even the final machining is required to achieve the right geometrical tolerances and as well as to get the required the surface finish or the required mechanical properties and all from these kind of the machines. And if you see with respect to the repair application, if something the worn out that can be repaired, these kind of the DED systems can be used to repair this such kind of application. And even some of the worn out turbine blades that can be repaired, and even you can add some of the functional aspects, the attachments to the existing part. The fins or the casted engine parts are some of the additional things that can be made with this the energy deposition technology. And when you comparing with all these metal IT manufacturing process to make the metal parts in the metallic printers, you see the comparing with the wire feeding technology, direct energy technology, and powder bed EOS, and as well as powder bed with the RCM EBM technology. You see the deposition rate is highly more in case of the VAM process, because we are having a wire feeding technology in the VAM process, because instead of the powder we are using wire. That we are having a high deposition rate, that is 9 kg per hour we can able to melt and deposit the component with the VAM process. But in the case of the DED, we can able to manufacture 2 kg per hour, that is the production rate we are having in the direct energy deposition process. But in the case of SLM with the EBM system or with the electron laser system, we are having 0.1 to 0.3 kg per hour of the production rate. Means the scan speed rate is very high in the case of the electron beam or in the powder bed systems, but in the case of the scan speed as the scan velocity is less in the case of the DED or in the process system. And if you see how this DED works, you might have already saw a number of videos, but if you see from the beam technology how this DED works, you see this is the coaxial nozzle we are having the nozzle head where the laser coming through the central axis and the powder feeding from this the coaxial nozzle. This is where the powder feeding that carried from this the inert gases, that is the argon gas we can use or the helium gas we can use, and where the melting is taking place by interaction of this laser and the powder that can be used to melt the n number of powder, and layers are formed by layer deposition is taking place to repair or to make the real-time components, the D components. You can see even this type of real components can be made near-net shape components, or even we can make highly. This is the gantry with along with the robotic head is used to make these kind of complex parts and all. And you can see any complex parts can be made with this process. Even you can add these additional features. As I told you, the additional fins or additional features can be added to the existing part. That type of the operation, that type of functions can be made with this direct energy deposition process. You can see this is the functional grade materials. We are varying the gradient of the materials from one layer to another layer. That functional gradient material can be varied from this kind of the process. Even the some of the case studies we will discuss with respect to the functional grade materials and all is worked in this DD system. This is some of the how this technology very much related to the close to the welding process. See, when the electric arc is generated even in the welding process, it is going to melt the whatever the feeding material, either the electrode or the additional filler material, and it is going to join between the two metals or the similar or dissimilar kind of material. That is kind of a TIG welding or MIG welding. In the similar case, this DED works because here you can feed the wire feeding system with the electric car. You can able to generate the arc and to able to melt, and with the required the speed or the deposition rate can be made with this kind of the process. And when you coming to the selective laser melting process, where we are having in our laboratory the 3D systems machines, you might have gone through the lab session. Even the tomorrow in the lab session, we are going to discuss more about how this 3D expert software works and how this metal 3D printing works, what all the components we have made, and also how it can be made. How we are giving some small the training with respect to the metal process. In this powder bed fusion process, this is the selective laser melting is a powder bed fusion process. It was accepted the ASTM terminology from the additive manufacturing process, where the point heat source selectively fuses or melts the region of powder bed. This is the powder is bed entirely powder is spread over the build plate or the build platform area. The point heat source, this kind of the laser beam point heat source is going to selectively melt the whatever the 3D CAD model design we are fed into the system. Based on that, the laser is going to melt the powders in the entire build platform area and all. And this process is also known as the direct metal laser sintering or the laser melting and all we can call. In this powder bed fusion system is the most frequent used technique wherever we need to have a parts which is very highly precise or the small components, very biomedical components with these kind of the techniques can be used. In this process, how it works, you can see there will be a two build platforms here. One is the powder carrier. From that, the powder delivery systems is roller or the blade is carrying into the a build platform area. Once the layer is sintered or the melted, the build head is going down, and then the second layer is going to deposit. This is how the function works in the powder bed system. In these powder bed systems, you can use laser as energy source or even electron beam as energy source wherever we need to have a higher building rate and to have the better surface quality and all. And that is also depends upon the choice of materials. We can use this kind of the energy sources and all. And this is the very promising technology for aerospace and as well as the biomedical applications and all. When you can see in this layer thickness 0.02 millimeter to 0.1 millimeter of layer thickness can be produced. And these layer thickness are very stringent, are related to the what kind of powder size we are using. As I have discussed in the yesterday's my session, how these powders are related to the process. We are using 5 to 45 micron. In such cases, we can build even the 10 micron layer thickness of the in this SLM system. And even if you are using 15 to 45 microns of the powder, the layer thickness can be made only with the 15 micron. Below the 15 micron cannot be made with that kind of, because the powder size itself is a 15 to 45. And it is the laser beam diameter will be 70 micron. That depends upon what kind of laser we are using. Whether we are using CO2 laser, NTAG laser, or the continuous fiber laser. And even with the laser beam diameter is vary from machine to machine system, and also the with respect to the capacity of machine system. And also the average powder size particles will be 35 micron. That depends how we are using, whether we are using 5 to 45 or 15 to 45. And if you see with respect to 3D systems, what we are having in our machine laboratory, you can see this is how the roller takes the powder from the hopper to the build platform area, and then the laser is melting the whatever the tool path strategies, that is the 3D CAD model given to the system. There the laser melting is taking place. And it's going to build the melt the materials of the single layer, and then again when the second roller is passes going to deposit the powder material onto the second layer, again the laser is going to interact and fuses melt the materials in the same tool path strategies whatever we are given to the 3D CAD file. And this is how the parts are manufactured, and after that it is removed from this the powder bed systems using a vacuum cleaner or with the removing of the powders and all. This is how this the powder bed system works. You can see these are the examples are the parts which are made by this SLM process. And this is with respect to our laboratory we are made with the standardization to validate the machine setup. And this is with respect to other researchers they have published what kind of the components, what kind of the status, the porous structure struts, and also the lattice structures, and also this kind of porous, the nozzle leap engine jets are some kind of the ceramic materials, how we can able to manufacture with this kind of the SLM process and all. These the highlights of this SLM process, and this is a very simplified manufacturing process. The minimal post-processing dispatch the complex structures to avoid the tooling wear when the processing too difficult to machine the nickel-based alloys. And also the innovation with respect to this process is the direct integration of multiple parts and the internal features like the internal ducts with different lattice structures can be made with this the powder bed system. Even the efficiency is the minimization of the individual process steps while combining with the multiple individual parts into a single component can be made with this the modeling of this SLM process softwares. And with that, the production time is going to be reduced from months to the days when you are making such kind of the highly complex parts. And also the lightweight construction, because when we are using these kind of the lattice structures, topological optimized structure, definitely there will be a reduction in the the weight of the component. That is the lightweight construction will be having a considerable weight reduction due to the lattice structures and all. And with respect to the scenario of this the market situation and the competitive scenario of this AM process, you can see the leading manufacturers of these machines from this Europe, from the especially for the metal 3D printers from the US, or the Trump or the realizer are from the US, the concept laser now it is called as a beam, and also the SLM solutions, RCAM, Renisha, X1, the Phoenix systems. These are all the systems was the components was made from this. The additive manufacturing machines was made by these European companies and as well as US companies. And in this, the leading manufacturers for the aerospace and as well as healthcare sectors. And if you see in the right hand side, the market scenario from the 2014 to 2023, the requirement of these components in all the aspects, aerospace is growing, developing, automotive is developing, medical is growing, the dental is growing, and even commercial service and others is also growing day by day in these aspects of the especially the growth of these many sectors is 52% in the 3D systems and the RCAM is 43%. It's a technologically computations mainly involving in inline monitoring and as well as the quality control of the machines which are made by this the 3D printing and all. And in these there are so many industrial barriers are there. What we are talking about this the metal IT manufacturing process, we can say that it's a direct printing or near net shape manufacturing, whatever the complex parts are can be made. That is, you can say that, but there are a lot of challenges existing in this process. Not only the complexity is made with this process, even though complexity is high, we can able to manufacture, but lot of the manufacturing challenges are there because when we are using different kind of materials or the different kind of the process, the repeatability is a major issue, and as well as the limited stability, and as well as the parts which are made from one process to another process is also a not highly comparable because the quality aspects as well as the defect rate is very high in such cases of the parts are manufactured from the different AM process. You can see the defect rate is more than 5 to 30% of the defect rate because such type of components are not at all useful for the aerospace or the medical application because that issues are still existing that need to be addressed when the research is carrying out with respect to these kind of the AM parts which are made by these metal AM parts with the AM machines and all. You can see geometrical defects may be there, these kind of geometrical defects, and also some of the residual stresses. You can see these kind of the residual stresses are going to exist. The cracking or peeling is going to taking place, and the porosities, and also the porosity in contamination of impurities or foreign particles when the melting is taking place. That is all causes for the failure of the components. Even when the defect rate is not at all acceptable in the current state, there are it's a very long process and a long expensive trial and error implements is required from time to time markets and all, and it's a very stringent quality requirements is there in the aerospace healthcare. We need to have the stringent quality requirement because that cannot be used even if the quality aspects are failed when the certain limits. The defect rate is minimal, then only you can use. If the defect rate is going more, then you cannot able to use such kind of the parts from the aerospace applications and all. And if you see the what are all the process map with respect to the process challenges in the DED systems, the direct energy systems, you can we'll discuss what are the barriers or the challenges. Even in the SLM system or the DED system, you can see in what rate the energy density need to be set to make a highly efficient component. You can see this the graph shows us the laser power with respect to the scan speed. If you vary the scan speed or very high speed, it cannot be beneficial because it is going to melt too much of materials and going to generate so much of the gas bubbles or the trapment of the gases is going to taking place because of the excessive heat is going to generate these kind of the effects in the second phase in the zone 2. That is how we are having these kind of defects will be there. Even if you are having insufficient melting, the energy is less, the laser power is less, and even you are melting at high scan speed, you are having these kind of the defects will be there because the energy is not at all going to melt the layers. Insufficient melting is taking place, then these kind of defects will be there. Even if you are overheating these kind of defects, that overheating because of you are having a more amount of energy, the entrapment of the gas bubbles, these kind of defects will be there. That is why we need to have a fully dense means we need to have the optimization of this the process laser power and as well as scan speed required, how much of energy density with respect to the particular materials are required. And if you see the processing issue with respect to the DED systems, maybe a material issues, or it may be the built chamber atmosphere, or it may be the feed quality, or it may be the conditions, or it may be these powder issues, or any other issues also. If you see the material processing issues, like when the future size, the surface finish, and the geometric scaling is required, you can see the particularly layer thickness can be made with this 10 to 50 micron. Even with the DED systems, the 250 micron, and even with the DED wire system, we can make up to 3 millimeter of the layer thickness. And even with the minimum features, we can able to make 75 micron or 100 micron, and even with 16,000 microns can be made with this DED wire feeding system. You can see in the right hand side when the layers are deposited, these kind of the layer, continuous layer in the Z direction. This is the single layer. This is what we called as a staircasing effect, the stair stepping effect or staircasing effect. Because in the right hand side and on the left hand side, the layers are multiple layers are fused. Based on the layer thickness, we are going to have the staircasing effect. You can see in the 3D topography, this is what we called as a stair stepping effect or staircasing effect. Even in this, even the single layer, you can see, observe here how the actual surface roughness will be there in the metal surface, which is in the single layer itself. In the smaller layer thickness, you can see this is the unmelted powder particles will be there. These are all the struck unmelted powder particles in each layers will be there. You can see in the 3D view, these are all the unmelted powder particles will be there. These unmelted particles are the this kind of the shape the is going to affect for the successive layers, and that layer effect can be tried to minimize by increasing the number of layers. When you increase the number of layers, a time to build or fabricate is also going to be increases because number of layers are increasing, and the time for manufacturing is also going to be increases. And with respect to the other aspects, that is they build atmospheric conditions, especially with the DED systems. We need no need to have the some inert conditions, like whenever we need to have the highly oxidizing material, especially titanium, we need to have this inert atmosphere. But with respect to other materials, no need of that inert gas shielding is required, atmospheric conditions and all. But when the highly oxidizing material, the chemistry is strongly affecting, in such cases, we need to have the inert gas atmospheric conditions in the DED or SLM or in the EBM system. But in the EBM, we need to have a vacuum systems. Otherwise, the working is not at all possible in the EBM systems. And all. That will be having the vacuum pressure of 5 to 10 power minus 2 to 10 power minus 4 pascals of the pressure is required in the vacuum pressure in the EBM systems and all. And also this SLM is typically operates in the argon environment, that is in the inert gas environment. And the other aspect is feedstock quality. Feedstock quality, where we are discussing these GD systems, either we are feeding through the wire or from the external the injector, the feeding nozzle, powder is fed into the molten stream where the laser beam is interacting, or the radially symmetrical the powder injection nozzle, or the coaxial nozzle. These kind of the four varieties we are having in the DED systems. In this, the importance is the quality of the part is depends upon these kind of the nozzle feeding systems, and as well as the powder quantity. Or we are having the metal wire feedstock. Even how the energy is utilized to melt the wire or the powder, and what is the quality of powder we are using, size, shape, as well as the surface morphology, composition, and how the amount of internal porosity existing in the powder itself. That quality of powder is going to determine the physical variables like flowability, apparent density, all these going to relate the quality of the part. You see here the quality of the part before going to use. Means we make sure that the powder quality is efficiently good. Then only you can able to use in the DED systems or in the powder bed system. You can see these kind of the powders which are made by this water atomization or gas atomization. These kind of powders are highly difficult to use in the metal AM process because it may be flowing, not flowing uniformly. It may be stuck in the nozzle, or it may be damage the roller, or it may be unevenly, not homogeneously spread over the build platform area. That is all going to cause the defects in the part which are manufactured. That's why the product quality is directly related to the production techniques. Whatever that automation we have discussed, like gas automation, water automation, plasma automation, all these are all playing a major role in the product quality and all. And for the WAM process, wire arcade manufacturing process, the defects are minimal because when you comparing with the powder technology is not much the exaggerated or the well researched in the powder technology. But in the case of wire making, it is already available in the since so many years. It is available from the welding technology and all that it transferable from the mature to welding technology. That wire, same kind of wire we are using as a supply chain for this lamp process and all. That's why defects. But only with respect to the aluminum material with respect to VAM process are very challenging and all. And the other challenges with respect to the no contamination in the powders, nearly no moisture, and the size of the powder particles, shape of the powder particle should be uniform. No mixing of the powder charges or the reuse of remaining powder is also very much important in the powder when you are DED systems and all. And the other aspect is the powder and the beam interactions. You can see where the laser beam is interacting with the powder, there is so much of the ejection of the powder is taking place, scattering is taking place when the powders are observing the laser energy. That depends on what kind of powders we are using. And also, the some of the spattering is going to take place. Spatting is going to take place. This is all depends upon the what kind of the thermal conductivity and observability of the powder materials, and maybe reflecting due to the laser before it is inputting into the substrate or molten pools and all. That is how this the irradiation and with respect to the substrate and all this is going to taking place because of the convective transportation of liquid or vaporization of the metal of the melt pool and all. That is where the spattering ejection is going to taking place. Even with the electrostatic repulsion is going to taking place in the powder particles in the electron melting, and also in the DED kinetic recoiling is taking place in the DED systems, and also the enhanced convection of the powder in the gas streams. And all. This is what the powder beam interaction is going to be taking place in the case of the DED systems. And with respect to the porosity, this porosity is a very common issue in the metal AM process. If you take any SLM process or DED process, porosity is a very common issue. To avoid this porosity is or to negligibly minimize is highly challenging the AM process, because the porosity may be induced by the process or it may be induced by the powder or it may be during the solidifications. All these need to be addressed when you finely tuned the process parameters. And if you optimize the process parameters, the melting efficiencies, that is, you can able to minimize these kinds of the process induced. But if it is a artifact of the solidification, that one need to address with respect to the materials, the solidification conditions, and as well as the solidification profiles, and as well as the cooling rate and the thermal temperature gradient. And the other the issues with respect to the metal AM processes, the strategies, the scan strategies. As we discussed a number of process parameters, scan strategy is one of the major issue when you are making the materials, because if you are using these kind of the linear or bidirectional strategy, the material may be having so many number of residual stresses. To minimize the residual stresses, we can go with this kind of the chessboard or with the Highland strategies or with any other different kind of hatching strategy that will minimize the residual stresses, and also how efficiently it can be used to manufacture the part, not only with respect to the residual stresses, and also it aspects the quality, the geometrical tolerances of the part which are made by these different scan strategies and all. The Hilbert strategy or with the rotation with the 45-degree, 90-degree, any orientation, or with island scanning. This is all with respect to depends on the part geometry and as well as the what kind of how much the height we are manufacturing. All these are all going to play a major role in part fabrication. You can see the other the challenges is the cracking and delamination. These kind of defects is essentially depends on the process temperature, because the continuous repetitive cooling and heating is taking place. That's why the temperature accumulation is taking place throughout the build platform area. That temperature is going to affect these type of crackings or delaminations. That's why the cracking of this microstructure may occur during the solidification and because of the subsequent heating and all. Even the macroscopic cracks may be related to other defects, including the porosity and all. And the solidification cracks can occur for some materials if too much energy is supplied. and also arise from the stress induced between the solidified areas of the melt pool and the areas are yet to have to solidify and all. And even the delamination things are going to be taking place you can between the layers. If you are not sufficiently melting remelting the previous layers, these kind of delamination is going to take place. And this kind of the melt bowl formation is also going to be taking place because of the incomplete melting or remelting or incomplete remelting of the underlying solid layers, and also because of the variations in the scan speed and the power. These kind of the balling effect is going to be taking place because of the when you are using very higher scan speed rate, these kind of defects you are going to you can see here with respect to scan speed and power. Balling effect is where we are going to have a stable track when we are having humping, when we are having non-uniform with the weld beats and all. This is all based majorly on the scan speed with respect to the laser power. And this is the balling effect is very common issues even in metal AM due to a large thermal temperature gradient during the process, and it can be negatively impact the mechanical properties and act driving forces for the challenging in the grain structure and all. And if the stresses exceeds the local yield stresses of the material, then the metal wrapping or plastic deformation is going to take place in the printed parts and all. Even if the stresses exceed the local ultimate strength of the material, then the cracking or delamination defects are going to occur in the fabricated component. That kind of macroscopic residual stresses can be dramatic effect on the bulk behavior of the AM parts that need to be addressed by changing the strategies, that is the deposition strategies, or by the heat treatment process. For further heat treatment process can minimize those kind of the residual stresses in the components. You can see this kind of deformation is going to be taking place in the fabricated component. And this is with respect to the comparative, you might have aware all these things, how this the build reparation rate, the accuracy, what we are getting, surface roughness. Even DD is having a more surface roughness fine up to 500 micron, but in SLM you can get 10 to 50 micron in the fabricated components itself. And some of the case studies where we are going to talk more about this real-time aspects where we are using with respect to the DD systems or SLM systems in the aspects of this metal AM process. If you see here the relationship between these process parameters and as well as how this the thermal history, microstructure, and post processing is required to meet the stringent industrial parts, stringent requirement in aerospace or medical parts. The laser-based powder additive manufacturing system consisting of this n number of the process parameters, and as well as the thermal history is the peak temperature, melt profile, the cooling rate, and the fusion solidification, and as well as the surface texture, the microstructure, the porosity, the residual stresses, the deformation. All they are going to existing in the fabricated component, and then we need to have the post processing things. The post-processing things are the hipping process, or it may be the heat treatment process, laser polishing, and for the fit for the service properties is mechanical or corrosion properties, and these are all the component quality aspects, the post-processing and component quality aspects. And when you see the real-time examples, this was the air duct was made, air vent or air duct you can call, made with the ADD systems. This is in the small prototype scale was made, the stainless steel 316 steel material. In these DED systems, when we are using a coaxial nozzle with a concept laser, how we can, this is the designed model, and in the design model, we have varied the different laser scan speed and as well as laser power to make this kind of the air duct. And to manufacture that component, we use the DED systems with a water flow rate of the uh, 8 gram or even with up to mass flow rate 3.8 grams of powder per minute we used with the gas velocity and the gas flow rate 2.9 to 3.5 liters per minute, and the laser beam of 180, and as well the focal length is 300 millimeters of focal length. And this is the chemical composition of the stainless steel powder we used, and you can see in the optical images, this is in the build direction, and in the surface how the surface you can the surface are the unmelted particles are there, partially melted particles are there. Because of this, surface roughness we are getting is 500 to 600 microns of surface roughness is getting in the DED systems. But when you see in the initial layers, we are using very high amount of laser power too, because need to be successfully welded to the substrate and also need to be have a sufficient weld strength and all. And even at the top layers where we are using a very higher scan speed rate, that is at around 1300 scan speed rate, we are having these kind of the balling effects. You can see this is the balling effect, because the uniform weld weight is not at all going to come. In such cases, we are going to have this kind of the balling effect because of the higher scan speed rate and all. And we have analyzed how the rippling force and wavy surface going to affect the part integrity with these stitched layers, which is the successive layers. You can see this is the two-dimensional topography of the individual layers, which was manufactured from these DED systems. And you can see here, this is the melt profiles at different the scan speeds, and for a power of 180 laser power, you can see the melt profiles are going to vary. At higher speed, the melt profile, the size and dimension is going to be decreased. These are all going to affect the layer stitching, or you can say the successive deposition layers. You can see here the surface is layers are width is less here, and number of layers are 6. Even though number of layers is 6, where we are having highest amount of the laser with the less speed, we are going to have these kind of the increase in the wall width, effective wall width is increased. This is what is going to be taking place in the laser direct energy deposition process. And also the other aspects is the contact angle between the one layer to the another layer in the liquid metal. This is the contact angle between the solid wall and the liquid wall. That the contact angle is highly important, because on the rough surface the contact angle changes constantly from one layer to another layer. That affects the wettability property, and the spread in the deposited molten pool is going to take place. Because of that, wall thickness changes irregularly, and which is what we are expected. And the other aspect is, if you see here in this the image, this is what the number of layers are fabricated. Theoretically, we assume that all layers are uniformly fabricating, and we are going to have this uniform layer thickness and all. But when you see the layers are formed, you are having a discontinuity, or we are having these kind of the point defects. If you are having these kind of the point defects, we are having a variations in the focal length between the where the laser interaction and the laser surface or the layer which is deposited. If you are having these kind of the defects, then automatically going to affect the part which is going to be manufactured, because where is you are having the hill area or the valley area, that is going to vary the focal length. That focal length is going to vary. There, the successive good prevent manufacturing is not at all possible. That is where we are having the failures. That kind of system. That is why the online monitoring systems are required to address such kind of issues in the IT manufacturing process. And also, we have analyzed whatever the air duct, which are the air vent, is manufactured from this stainless steel material. The cross-sectional metallographic analysis of this some of the porosities were observed, and also the how this microstructure for the metallurgical polishing and hitching. You can see these are all the weld bands, or you can see the solidification profiles, solidification bands. This is where we are, and also the grain growth structures we are getting in this direction from the outer wall to the inner wall. Even you can observe here in this exaggerated view in the scanned electron images. You can see this is the dendritic, the cellular fine microstructure dendrites are available in the center of the fabricated wall, and where the layers are successfully melting and solidifying, remelting is going to taking place. This is how the bands are formed. The fusion bands are formed because of the repulsion and the contours of the walls. We're going to have these kind of the bands are formed, and also these kind of the cellular dendritic structures are formed in the fabricated components. And also you can see here in the challenges and facts with respect to this metallurgy manufacturing process. You can see in the left hand side and the right hand side, the convex and concave multiple profiles are there. Why we are having this convex and concave multiple profiles? These convex and concave multiple profiles are because of the variations in the energy density or change in the energy density. When we are having the energy density is less, which is not able to remelt the successive fusion layers, these kind of the defect or these kind of the solidification profiles we are going to get. When the sufficiently using the energy density, we are going to have this kind of the multiple profiles. When the multitude of this complex interaction between this physical phenomena, that is the heat transfer, fluid, continuum mechanics, the melting and solidification, and the solid state transformation, the grain growth, and the diffusion of this texture is going to take place. There are many other process variables that is related to the energy, not only the laser power, trial speed, even the feedstock of the wire or the feed or the ribbon, and also as well as the deposition parts. That is the we are using different scan strategy parts are there. Right? That is also relating is the solidification profiles, or the change in the dimensions or the deposit characteristics and all. So see here how this balling effect or the puckering effect when we are calling about the welding. When we are having these kind of defects, the balling effect or puckering effect, these kind of the capillary instabilities are going to occur in the AM process. When the diameter with respect to the length ratio is greater than the pi by 2, we are going to have no balling effect. When it is less, we are going to have the balling effect. That is, the L by D ratio we are having more than the 2.1, definitely we are going to have this kind of the balling effects. And if you see, this is the simulated results where we are having balling in the selling process. This is the instability in the melt pool. When the instability is the melt pool, there is no uniform wetting angle. There is no uniform wetting is taking place. This type of the balling effect is going to take place because of the hydrodynamic instability. When the Maragoni flow, the Maragoni effect is going to take place inside the molten pool, where the higher the concentration of sulfur or oxygen in the stainless steel, when the ferrous, in that type of hydrodynamic instability is going to create this kind of the balling effects. And also the splashing of the molten melt pool due to high surface temperature and as well as the turbulent flow in the solid liquid interfaces and all. And even in the welding, you can see these kind of the puckering defects the observed in the welding and all. And you can see the positively skewed particle size distribution containing a high fraction of smaller particles, resulting into a smoother the contour of the melt pool than the negatively skewed one containing a high fraction of larger particles. And the formation of this balling effect from a void at the center of the molten pool. As the void expands, the molten pool breaks and apart into a separate island. There you are going to have this kind of. And as the faster travel speed and lower laser power can also increase the likeliness of this forming of this balling effects. And if you see the microstructural aspects when it is resulting with the welding science, this is how the solidification is taking place even in the pig welding or in the MIG welding or in the metallurgy manufacturing process. The dendrites are growing from outer wall to the inner wall. This is all depends upon the temperature gradient and as well as the solidification rate, or you can say the cooling rate and all. When we are having a highest temperature gradients, we are having these kind of the dendritic structures. And when we are having a lowest temperature gradient, we are having these kind of the dendritic structures. This is where we are having a lower L by G ratio or the higher G by R ratio. We are going to have this kind of the dendritic columnar structures, and also at the center we are going to have a equiaxial dendrites. You can see in this central zone we are having a equiax dendrites can be observed because the solidification rate is slow in the central portion compared with the outer boundary or outer surrounding area. And the solidification rate is slow, we are going to have that kind of cellular dendritic structures. These kind of the cellular structures can be observed in the materials, even in the welding of the TIG or MIG welding conditions also we can able to see. And the how we can able to control this grain structure by the deposition rates. See, one of the researchers have tried with respect to the varying laser, the powder flow rate and the deposition rates with the same constant laser power and as well as the scan speed. They have made an attempt because when you are supplying more amount of powder, the energy density is going to be stable. That the energy is required to melt the material is going to be vary when the powder is increases. That's why even if you supply 6 gram of powder, 11 gram of powder, 15 gram of powder, 25 gram of powder, 31 gram of powder, or 44 gram of powder, or 55 gram of powder, you are going to have variations. These kind of variations will be there when we are having a varying the powders. This kind of microstructure we are going, you can see here the average fraction percentage even with respect to the depth with respect to the columnar mixed grains equiaxed grain. These kind of variations can be observed in the varying the laser powder quantity and all with respect to the uniform the laser power and the scan speed rate and all. You can see these kind of the dendritic growth is taking place from the substrate to the uh, towards the build rate, build height, and as well as in the surface, we are going to have equiax dendrites. We are going to have these kind of things. These are all the fusion lines where you can say the fusion bands or fusion lines, and there will be a heat affected zone. This is how the grain structure controlling grain structure with respect to the deposition rate. And we have also evaluated the microstructural evaluation with respect to the voids in the fabricated samples. You can see that throughout the build deposition, we are having this kind of the hardness. Even some cases, we are having a increase in the wear hardness. That is due to defects or maybe phase changes with respect to the formation in the stainless steel, austenitic stainless steel and all. And also, we have studied the surface topographical aspects. See, in the manufactured samples, definitely the surface roughness is very high. Even we are getting 500 to 600 micron surface roughness in the even in the internal curve or in the external surfaces of the fabricated air duct. But how to minimize those surface roughness? So to minimize that, we need to have the post processing. We have tried with the laser polishing process to minimize that surface roughness from 500 to less than 10 microns of surface roughness can be made with this laser polishing process. Even with the internal surfaces can be made with the laser polishing process. Even nowadays we are having so many advanced post processing techniques, chemical post processing, the electrochemical or with the electrochemical etching, even with the abrasive flow finishing, magnetic abrasive flow finishing can be used to polish this the manufactured samples and all. And the post processing is very much required wherever we are having a very rough surface finish, and that the post treatments partially necessary, especially in case of the need of inspection, the penetrate testing and all in such cases is required. Even mechanical or chemical milling methods are also applied, and for wherever the high load carrying capacity, the hot isostatic pressing is a mandatory to eliminate the pores or to remove the defects with the nitrates or oxides or carbides, and to dramatically increase the material's mechanical properties, we need to go for the HIPIC process. Even though it is a costliest and expensive process to get the required heat treatment shipping process, we need to go for this, especially for the metal AM parts. And we have also analyzed this EBST analysis. You can see the EBST results in the horizontal cross section or in the build direction. You can see in the build direction, we are having a elongated columnar dendritic structure that is in the plane towards, this is how the crystallographic orientation you can able to see 001 plane as well as 11 plane, 101 plane, in both the horizontal and as well as the build directions. And we have compared the mechanical properties with respect to the rot alloys and as well as the fabricate with this 3D printing process with the direct energy deposition process. The rot alloys having a highest tensile strength as well as elongation properties. But when you come up with the ultimate manufactured samples, the strength is almost equivalent or even more than the raw tallest and all. But the elongation properties decreased very more, reduced in the elongation properties or the ductility because of these kind of the defects in the fabricated parts. That is the unmelted particles or porosities are causes for the reduction in the elongation properties and all. And you can see the reduction in the ductility is because of this kind of the unmelted particles. It will be there in the defects. This kind of defects are going to cause us for porosities are going to cause us for the reduction in the ductility of the fabricated AM parts. And the other applications we have tried for repairing applications. We have used this the DED process to repair the functionalized parts. With the help of this inconel or with the monel materials, we have repaired on the existing monel for a wide range of oil and gas aerospace applications. We need to have this kind of materials to increase this chemical corrosion resistance to enhance the properties. We have tried to repair that. You can see in the repaired zone, you can see the melted zone intercrystal materials, how the grain structure orientation is taking place, and how this is going to be taken place in the materials. And you can also see here how this microhardness variation is taking place when we are repair such kind of the parts. The hardness with respect to the depth. You can see the variations from one layer with respect to one material to another material where the transition zone is taking place. In this around 400 to 600 zone, this is the transition between 625 to the monel material, defined monel materials. This reduction in the 100 in the zone will be because of the heat affected zone. And also you can see this DED process can be used to repair applications. You can see chromium is deposited on the stainless steel material, where in the interface zone we are having a increase in the hardness properties in the such cases of the chromium and stainless steel materials. And also you can able to see the microstructure, and also the in the austenitic phases where the interfaces will be there. There will be a lot of changes in the metallographic properties and all. And also we have tried how we can able to address the energy. So energy density is going to affect the variations in the geometrical aspects. That geometrical aspects in terms of the Z height at 1 kilowatt, 1.5 kilowatt, at 2 kilowatt, how it is going to be varied. You can see the we are keeping the constant of the powder flow rate of 18 gram per minute, and as well as the scan speed of 1500. Only we are changing the laser power and how we can able to monitor. We need to have the feedback monitoring systems to coincide this temperature, width as well as height, because knowing that the bead is not regular inherent to changing this interfacial, the angle or the on the rough or the contaminated surfaces or before the underneath layer, you can see the layer height or width is going to vary with respect to the laser power here. You can see in the table for 1 kilowatt is 31 and for 1.5 kilowatt is 30 and for 2 kilowatt is again 28, because even we are succeeded, we are assuming that 75 layers of 0.5 millimeter thickness is going to be calculated, but even such kind of these defects are going to be occurring because of the variations in the energy densities. Because of that, the surface waviness, contact angle, we are accumulation of heat. That heat energy is supplied to the melt pool. That's why when we are making the fabrication of the process, these kind of defects are going to occur in the fabricated. Because if you're not optimizing the laser energy density, these kind of the defects, even the metallurgical defect like the convex melt profiles, convex melt profile, when we are having less amount of energy density, the elongated columnar structures and as well as the shift in the orientation grains is going to, even the direction of orientation is from inward to outward is going to be taking place here. But here, if you have sufficient amount of energy density, outward to inward is going to be taking place in this case of. This is what we are expecting the concave multiple profiles, and through the build direction, the grains should be oriented. Here we are having a highly good mechanical properties in the fabricated component. And you can see the other the analysis was made how this the strategies are affecting to make the fabricate the solid cylindrical blocks. You can see we have made some of the solid cylindrical blocks with the different hatching strategies. That is with the linear bidirectional, or zigzag bidirectional, or with the circular or spiral strategies. You can see these are all the different strategies. This, if you're using linear or linear bidirectional strategy, we are having these kind of the geometrical defects in the surface. This, even in these kind of geometrical defects are good. Even with the spiral or concentral, using these kind of the surface defect, geometrical defects will be there. But to address those things, how you can see the strategies are there here. In these strategies, this is the linear strategy, means this the to make the cylindrical component, solid cylindrical component we are using, and this is how the components are manufactured. This is how the components are manufactured. Why we are having these kind of the geometrical defects? Because of the accumulation of heat. Even in the metallurgical aspects, the porosity or lack of fusion is taking place, where the successive start and stop is going to take place from each layers. Here you can see the start and stop is going to take place. In this zone, we are having so much defects. And when you taking up this the spiral, the molten pool is flowing from one direction to another direction. This is where we are, and where we are having the linear bidirectional, we are having the intersection between the one layer to another layer. There we are going to have these defects is going to take place. That's why we need to address. Once if you optimize the process strategies, then only you can able to avoid such kind of the defects with these strategies, and efficiently able to manage this kind of the components. And other, with respect to the titanium materials, we have tried and we have addressed some of the novel application parts or aerospace application parts. This is the titanium powders which are used 45 to 90 micron, and this is the chemical composition, the titanium powder. And with that, the surface topography was achieved even with the DED systems. RE of 20 micron we achieved, and the RZ of 140 micron. And we can see this is how the surface roughness will be there in the fabricated. Even with that titanium materials, this much of surface. With respect to microstructural, sorry, any queries? Hello, is there any queries? If you see the microstructural analysis or aspects of this cross section, the titanium components which are made by this the DD process, that is the laser metal deposition process, you see it can represent the number of layers and as well as the multiple profiles, and also the with respect to the width and as well as the layer height from bottom to the top. The not much variations in the layer height or layer width is going to be observed when you optimize the process parameters. And also the other aspects, if you see here, the microstructural properties, we are going to get almost similar to kind of the casted or the rod arrays and these kind of the alpha colony structures and the beta trans structures. These kind of the micrographical structures can be observed even in the titanium manufactured from the laser direct energy deposition process and all. And the micro harness was analyzed, the fabricated, stress relieved, even stress relieved at different inclination of the laser deposition, that is 45-degree inclination, or with the vertical deposition, or with the horizontal. With respect to all that, the variation is very, very less, between 350 to 430. The variation in the hardness was observed from the depth, from the top surface to the till the depth. And we have extracted the samples for the different orientations or locations when it is fabricated at fully laser metal deposited, or 50% laser deposited at the 45-degree, or with perpendicular, or fully wrought alloys, or with fully horizontal direction, or with the repaired at one side, or with the repaired at both sides. We have extracted the samples from the fabricated blocks, building blocks and all. From that, if you see here, the tensile testing was analyzed. These results, if you see, show that the strength are almost same. The tensile strength, ultimate tensile strength, are almost equal to the rod alloys and all. If you compare with any directions or any repaired applications, also the tensile strength is almost same. But when you checking with the elongation, the rotor having a very high elongation properties, but with respect to the AM fabricated LED fabricated will be having a less elongation properties. Even in the horizontal direction, vertical direction, 45-degree inclination, even in the repeat will be having less elongation property. Because we are having a defects, even youngster models are almost same. Defects, if you see in the factorographic analysis, these kind of the defects, the lack of fusions, the porosities are causes or unmelted pore particles are stuck inside the material. These defects are causes for the decrease in the elongation or the ductile properties of the fabricated titanium components in the LDD process. And also we have tried and we have analyzed the fatigue properties, the low cycle fatigue properties we have analyzed, and also the crack propagation properties also we analyzed for the titanium samples at different orientation and different building directions. It is almost similar to the rod alloys or the rod components. You can see here the properties are almost acceptable in consideration of this the fatigue properties or crack propagation properties and all. Can even the crab population properties are more than that of the rod alloys can be observed in the eight manufactured titanium samples and all. And with respect to other, the functional grade materials were made with this the DD process. Even with we have tried with these kind of the functional inconel or the 625 or monel materials or stainless steel aluminum materials. We have tried the different stainless steel with the satellite linear changes variations in the each layer deposition was made. The effective transition is limited to the mid height, and also the last segment buildup of consisting of the traces of this iron when you are using the satellite and as well as stellite and as well as 316. The gradual dilution effect were also observed because this is the influence of the feedstock and the process parameters. That is the laser beam, beam size, the scan speed, and the path. It is deposition rate also going to be identified in these aspects. These kind of the functional grade materials are manufactured in the ADD process. And you can see this is stainless steel with respect to titanium materials, and this is with the stainless steel and the stellite materials. And these kind of the impellers are with the air duct, and these kind of the components are made with these injectors are made with these kind of FGM components were made with the AD systems and all. Even if you see here the titanium and stainless steel materials and as well as stainless steel and nickel materials with the powder bed systems or DED systems, how we can able to manufacture the components. You can see how the tensile samples were extracted in these FGM components, and then we have studied the quality aspects or mechanical aspects. You can see in the if you this is one of the collaborator studied this titanium with the titanium carbide incorporation in the FGM systems. These kind of FGM systems are fabricated. You can able to see these kind of the dendritic structures and as well as granules of this titanium carbides are present, and as well as beta titanium and alpha titanium are present in these kind of the fabricated structures. These kind of the microstructural going to get it from when you are fabricating FGM of this titanium carbide at different locations. You can see this, and also if you see the tensile properties when we are fabricating titanium with the titanium carbide composites by varying the volume fraction. If you see at 0%, we are having highest tensile strength. When you are having 5%, the tensile strength is more, but the ductility is going to reduce because the formation of these carbide particles in metallic phases. That's why you are having increasing the tensile strength, but the ductility is going to be reduced. But even if you increasing further more of this the titanium carbide, it is going to decrease the tensile strength as well as the ductility properties. But if you see the hardness, when you are varying increasing the TAC percentage volume fraction, definitely the hardness is increasing because the carbide or formation of these phases are these kind of the eutectic granular phases that will cause us for increasing the hardness properties. And from this, if I conclude or summarize, the what all we have tried to address, the finite element energy, fine tuning energy is required to avoid crack defects in the fabrication parts or the functional repairing parts, and little or no dilution from the base metals and that. And also some embedded powder particles are there. That embedded powder particles can be observed in the last deposits. When you control the scan speed, that can be minimized. Even the particle-free lower deposits indicate the incomplete melting also, and also some oxide traces will be there. There are large number of variables like power density, powder flow rate, displacement, velocity, substrate characteristics that exert an important influences that are the resultant microstructural phase composition and properties of the same materials. This flexibility is also present in an inherent challenge when the need of optimizing the multiple variables is required in order to attain the reproducible properties for this specific material systems and all. And it is also evident that the AM technology can be used to manufacture almost infinite combination of alloys, metals, or ceramics or composites in very different geometries can be made with this direct energy deposition technologies and all. And some of the challenges are like online monitoring with the in situ sensors are required, and the integration and synchronization of image acquisition systems with machine controllers are required, and also the big data streaming management with the continuous process monitoring is required, and also the study of multiple sensor data fusion methods to enhance the process monitoring performance is required, and also the coaxial off-axis sensing. We are using the coaxial is the efficient, but in the coaxial itself is the melting efficiency is only 40%. The DED system that need to be improved to have the 80% of the melting efficiency. That's why the process monitoring the systems are required, and also evaluation of the novel in situ sensing solutions are required in these challenging developments of this metal additive manufacturing process and all. And I will stop at here, and also I need to address some of the WAM processed components. There is only 20 minutes of time, that duration of time I'll try to address the challenges with the components which are fabricated by in our laboratory with the DD systems and as well as the WAM process. You can see these are all the impellers or the turbocharged ship wheels, and also the implants are the turbine blades, repair turbine blades, and you can see these kind of the thin walls and different kind of gear structures are made with these DD systems. And with respect to WAM process, I'll just brief about the WAM process, what we have tried and what is the capability of WAM process. In this WAM process, it's similarly like a arc welding heat source we are using, where we are wire as a feeding as a raw materials. It greatly reduces the cost of manufacturing when you're comparing with any kind of metal AM process. Not only the SLM process or DD process, it's very highly the cost reduction process, and also the efficiency, the process manufacturing production that is very more. However, going to the surface finish is very poor in this case, because you see the surface finish is very poor. This is the WAM produced component, but further when you followed machining process, you can able to get this kind of. This is the die cavity which was made by this WAM process. And there are some of the examples which were made in the wire arc manufacturing process with stainless steel material, titanium materials, and wherever we are having intersections, you can see these kind of junctions, intersections can be made and can be machined, can be seen this kind of efficiency, and the stiffness panels can be made with this WAM process and all. And this is the final finished components of the WAM component. And you can see even with at the inclined angles from 0 degree and from 180 degree, and even with the 30 degree, 80 degree, that CMT torch, that is the continuous metal transfer torch, can be inclined at variations angle, that can be made with this. Even with the thin walls of titanium can be made with this, from medium to complexity 2D parts, even the weight reduction efficient parts, these kind of parts, even with the mixed materials, the functional parts can be made with this WAM process. And the WAM capabilities, we can able to manufacture titanium, aluminum, refractory, invar, steel, inconel, bronze, and copper. These are all the metals have already tried with this WAM process. Still, so many opportunities are there. When the researchers can address the difficulties or interesting areas where we can work out with this WAM process. You can see how this WAM works. This is the laboratory we have tried with manufacturing of some of the complex parts. You can see here, this is how we are using the robot to manufacture the component with the aluminum materials. You can see this is the arc we are using to melt the wire as a feeding material, aluminum wire feeding material, and this is how the robotic system works to make the components. You can see some of the components, steel parts are made with the WAM process. This is the ship propeller are some of the complex parts made by this process. You can see this is with our laboratory. We have made some of the impeller, the highly complex parts with the aluminum materials, and all we have tried and we have addressed the issues. You can see the air duct I was telling, the door of the aircraft, steel aerospace made with this part, and then with the VAM process with aluminum material, they have tried to address the replacement of this structural parts of the aerospace. And in the VAM process is also similarly from CAD to the printing is going to taking place. Once the part is printed, there need to be inspected using the laser scanning that can be addressed inspected in the part. And in these systems, we are having 5-axis systems, even with the 3-axis systems, we are having that need to be addressed which axis systems is going to be efficient. Even if you see, if you want to make, manufacture this kind of part, if you take from the block to machining, 91% of metal is wasting. But if you considering AM process, only 13% metal is wasting. That is the efficiency of this VAM process to make this kind of the components. And in this VAM also the deposition rates, the path process parameter, what is the heat source, so that is the current and voltage, also going to address this AM parts qualities and all. When we are using 3-axis or 5-axis, that depends upon the inclination angle, what kind of the tool, the inclination angle, the cone angle, 30 degree or 10 degree, we are going to manufacture, and that material maximum defects can be observed with the 3-axis and as well as the 5-axis. You can see the maximum defects was arrived in this 3-axis and less than in the 5-axis. When you are increasing the angle, if your angle is 10 degree, 15 degree, in both the axis, the minimal defects can be obtained, but the angle inclination is going more than 5-axis is the best one to have that. Also, the process control in the VAM process, it is uses the MIG control process, and how to eliminate this the porosities, because gas porosities are the most common processes in this wire feeding systems in the VAM process. Because when you are using wire, we tried to one of the researchers, William Stewart, has addressed by the interpass rolling. As deposited, you can see how much porosity is heat treated, and as well as the interpass rolling heat treated. We are going to negligibly reduce the porosity in the VAM components. You can see this is what I was telling, the interpass rolling in this deposition and interpass rolling is taking place. This is how the part is manufactured with the interpass rolling, that will minimize the porosities in the majorly in the VAM components and all. This is what the patent was taken by this Cranfield University. William Stewart was invented this kind of process, but it is limited to the linear components. But when it is a complex component, it is not at all possible to use this kind of the process with high pressure rolling and all. That will improve the even with the microstructural aspects. You can see at 50 kilonewton rolling, we are going to get 31, 39 microns of the size of the grain structures. At 75, we are going to have 66 microns of the microstructural grain sizes and all. Even you can see the different the multi-materials, the steel and bronze parts also made with this VAM process, and with the copper and steel with the tungsten ceramics are added to make this kind of the multi-material components with the VAM process. And this is what the benefits and limitations of the VAM process. You can see, if you see this the spider diagram, in this depends on what kind of requirement. If you want to have the uh, if you want to have the part size, platform flexibility, you need to go for which process. And if you want to have the cost saving, and if you want to have a highly mechanical properties or material utilization, we need to go for which kind of process. You can see the powder bed where we are having complexity and accuracy. And if you want to have the material mechanical properties, the material utilization, cost saving, we need to go for the VAM process. There, depending on this requirement, this the spider chart, we can able to use the process for a particular applications depending on the complexity, part size, platform, or the mechanical properties and all. And this is with respect to conclusions of the VAM process. The VAM is able to manufacture solid large scale structures in refractory materials by the fusion process. VAM is able to create a functional grade structures by is a controlled way process. And also VAM is able to control the evolution of the microstructure by monitoring the thermal cycle during the deposition. VAM is also able to improve and manipulate the mechanical properties using in situ cold working and all. And VAM is able to obtain a highly potential massive cost saving process in all the additive manufacturing, metal additive manufacturing process and all. And you can see we also simulated how this the stress deformation is taking place. When it is deformation is, or if it is welded at one conditions, you can see the welding is taking place, the layer deposition. If you are not welding at another conditions, here we are having a lot of the thermal stresses are going to occur. Here we are having a lot of deformation. The stresses are going to occur in that component. I'll stop at here. If you have any queries, I'm happy to address your queries. Thank you for patiently listening my lecture on this the metal additive manufacturing process and case studies and all. Thank you all.
Yeah, thank you, Manjaiah garu. Hello.
Participants, if you have any queries,